Around 13.8 billion years ago, singularity expanded violently in an event we call the Big Bang. Contrary to its name, the Big Bang was not an explosion into space, it was the sudden expansion of space itself. Within a fraction of a second, the universe ballooned from subatomic size to cosmic proportions. Temperatures soared beyond 1 trillion degrees. As the universe expanded, it cooled. Within the first few minutes, the first atomic nuclei formed, mostly hydrogen and helium, with tiny traces of lithium. This early phase of cosmic chemistry is known as the Big Bang nucleosynthesis, and it created the raw ingredients from which all future stars and galaxies would emerge. For nearly 380,000 years, the cosmos remained glowing plasma, a vast ocean of energy. Then came a quiet transformative moment. As temperatures dropped to 3000 Kelvin, electrons combined with nuclei to form the first neutral atoms. The universe became transparent for the first time, and photons streamed unhindered across space. That ancient light still travels today, stretched by billions of years of cosmic expansion into the faint microwave glow we detect as the cosmic microwave background, a relic image of the universe's first light. Now, gravity began to take the lead. Over millions of years, hydrogen and helium gas drifted together, forming enormous clouds. Where matter concentrated slightly more than average, gravity pulled in even more. These growing clumps grew hotter and denser at their centers until, eventually, nuclear fusion ignited. The first stars were born, known as Population 3 or the first-generation stars, massive and short-lived giants made almost entirely of hydrogen and helium. Their intense radiation and violent deaths reshaped the infant universe. Inside these first stellar furnaces, the next generation of elements was forged. Some Population 3 stars could only use the proton-proton chain to fuse hydrogen into helium, while more massive Population 3 stars were hot and dense enough to start the triple alpha process, which fuses helium into carbon. Through nuclear fusion, hydrogen fused into helium, helium into carbon, and carbon into oxygen, silicon, and iron. When these early stars exploded as supernovae, they scattered these heavier elements, the building blocks of planets, water, and life, across space. This was the beginning of cosmic diversity. The universe now contained not just light and gas, but chemistry. In the ashes of dying stars lay carbon for life, oxygen for air, silicon for rock, and iron for cores. Out of stardust, the potential for everything, including Earth, began to emerge. Across the next few billion years, these stellar remnants and enriched gas clouds would gather into galaxies. One of them, a modest spiral called the Milky Way, would host an unremarkable arm of gas and dust, where, billions of years later, a yellow star and a small blue planet would be born. But before Earth could exist, the universe had to build a workshop, a galaxy capable of forging stars and recycling matter. That is where our story next turns, to the alchemy of stars, where the elements of life were born. When the first stars ignited, the universe changed forever. Before them, there had been only hydrogen and helium drifting through the darkness, simple atoms without complexity. With stars, the cosmos learned how to create. Inside these enormous spheres of plasma, gravity and pressure performed a delicate dance. The immense weight of a star's own mass pushed inward, while the energy from nuclear fusion pushed outward. At the core, temperatures soared above 10 million Kelvin, enough for hydrogen nuclei to overcome their mutual repulsion and fuse together. This process, nuclear fusion, was the beginning of cosmic alchemy. Every second, countless hydrogen atoms merged to form helium, releasing energy as light and heat. That light poured into space, illuminating the cosmos and filling it with radiation that would one day warm the surfaces of planets like ours. But stars are not static furnaces. As they age, their internal chemistry evolves. When hydrogen in the core runs low, gravity takes over again, compressing the star further and igniting new cycles of fusion. Helium atoms fuses to form carbon, carbon fuses into oxygen, then neon, magnesium, silicon, and finally iron, the most stable element formed in stellar cores. These nuclear reactions inside stars are the reason everything around us exists. The calcium in our bones, the oxygen we breathe, and the iron in our blood were all forged in stars. As Carl Sagan famously put it, we are made of star stuff. However, even stars have lifespans. The more massive a star, the shorter and more dramatic its life. The first generation of stars, the enormous population 3 giants, may have burned for only a few million years before collapsing under their own gravity. When these titans died, they didn't fade quietly, they exploded in spectacular supernovae. In these explosions, temperatures briefly exceeded 1 billion Kelvin, unleashing a final wave of nuclear reactions. In mere seconds, elements heavier than iron, gold, uranium, silver, were born. The violent blast scattered this stellar material far across space, enriching the surrounding gas clouds. This process, called stellar nucleosynthesis, transformed a chemically simple universe into a complex one. Over billions of years, countless cycles of star birth and death gradually increased the abundance of heavy elements, what astronomers call metallicity, in the galaxy. Each generation of stars left behind the ingredients for the next. Some collapsed into neutron stars or black holes, while others seeded the interstellar medium with dust, microscopic grains of silicates, carbon compounds, and ices. These grains drifted in vast molecular clouds, waiting for gravity to call them together again. By the time our solar system began forming about 4.6 billion years ago, the Milky Way had already been through many such cycles. The gas cloud that gave rise to our sun and planets was therefore rich in the products of earlier stars, the ashes of countless stellar lives. In these cosmic remnants lay every element essential for life: carbon, nitrogen, oxygen, phosphorus, and sulfur. The universe had now written its periodic table. What remained was to assemble these ingredients into worlds. The story of Earth, therefore, begins not on Earth at all, but inside stars that lived and died billions of years before the sun was born. Next, we follow that stardust, as it gathers into a spiral galaxy, our home, the Milky Way, where a small corner of the universe would soon begin crafting its own solar system. Stars are the universe's forges, but they are also its engines of destruction. Every birth of a star sets in motion its eventual death, and in those deaths, the universe becomes richer, more complex, and more capable of creating worlds like ours. The first stars, the population 3 giants, were enormous, some more than 100 times the mass of our Sun. Their immense gravity made them burn furiously bright but live fast and die young. Within just a few million years, their fuel ran out. When a massive star exhausts its hydrogen and helium, its internal balance collapses. Gravity crushes the core, while the outer layers, suddenly unsupported, plummet inward at astonishing speeds. This implosion triggers a final cataclysmic event, a supernova. In less than a second, the collapsing core rebounds violently, creating a shockwave that rips the star apart. Temperatures in the blast reach billions of degrees Kelvin. In this inferno, atomic nuclei are slammed together to form new elements: cobalt, nickel, gold, uranium, all in a cosmic instant. The explosion hurls these elements into space at thousands of kilometers per second, scattering them across light years of emptiness. What was once a single star becomes a vast expanding cloud of enriched gas and dust, a supernova remnant. These glowing remnants, such as the famous Crab Nebula or Cassiopeia A, are the fingerprints of stellar death. Supernovae are both destructive and creative. The shockwaves they unleash compress nearby gas clouds, sometimes triggering the birth of new stars. Thus, in the universe, death often leads directly to creation. Each new generation of stars is born from the remains of those that came before, a continuous cosmic recycling that has been unfolding for more than 13 billion years. Among the debris of supernovae, dust forms, tiny solid grains of silicate, carbon, and ice. Though each particle is minuscule, no larger than smoke, together they fill the spaces between stars with a delicate haze known as the interstellar medium. It is this dust that scatters starlight, giving galaxies their soft glowing appearance. Inside these grains are the raw materials of planets, the silicon for rocks, carbon for life, and iron for planetary cores. Over millions of years, this dust drifts through the spiral arms of galaxies, collecting into vast molecular clouds. These are the wombs of new stars and, eventually, solar systems. Without supernovae, the universe would remain a barren sea of hydrogen and helium. There would be no carbon to form life, no oxygen to breathe, no iron to forge planets. Every atom in your body heavier than helium, every bit of calcium in your bones and iron in your blood, was born in the heart of a dying star. Astronomers studying the composition of the solar system have found that some of the isotopes in meteorites bear the unmistakable signature of supernova material. That means our own sun and planets were formed from the ashes of many such explosions, blending the remains of countless ancient stars. When the Milky Way was young, it was full of these fiery deaths. Each explosion added its color and chemistry to the galactic tapestry. Among these clouds, about 4.6 billion years ago, one region began to collapse under its own gravity, a swirl of gas and dust that would become our solar system. But before that, the galaxy itself had to take shape, a structure of stars, dust, and gravity where new systems like ours could be born. Long before the Sun or Earth existed, our galaxy was already ancient. The Milky Way, a vast spiral of stars, gas, and dark matter, is thought to be more than 13 billion years old, nearly as old as the universe itself. Within its glowing arms, entire generations of stars have lived, died, and been reborn. It is, in every sense, a cosmic ecosystem, recycling the ashes of stellar death into new beginnings. Astronomers believe that the Milky Way began as a collection of smaller, irregular galaxies and star clusters that merged over billions of years. In the early universe, gravity pulled together regions dense with hydrogen and helium gas, forming the first primitive galaxies. These small structures collided and coalesced, growing larger with each merger, until one of them, through countless cosmic interactions, evolved into the majestic spiral galaxy we call home. At its heart lies a supermassive black hole, known today as Sagittarius A, containing about 4 million times the mass of our Sun. Around it, more than 200 billion stars swirl in elegant orbits, tracing luminous spiral arms through a disk over 100,000 light-years across. Between these arms flow vast clouds of gas and dust, the fertile nurseries where new stars are born. The Milky Way's spiral shape is not static. It moves and breathes. The density waves that define its arms compress gas as they pass, triggering star formation in great and glowing clusters. These bright newborns, often blue and hot, illuminate their surroundings, the same kind of massive stars whose violent deaths enrich the galaxy with heavy elements. Our own solar system would one day form in one of these spiral arms, specifically, the Orion Arm, a relatively calm and middle-aged region located about 26,000 light-years from the galactic center. This position, often called the galactic habitable zone, proved to be just right, not too close to the violent core where supernovae and radiation are common, and not too far out where there is little material to form planets. By the time the gas cloud that birthed our Sun began to collapse, the Milky Way had already experienced billions of years of stellar evolution. Countless supernovae had seeded its spiral arms with carbon, oxygen, silicon, and iron. Each new generation of stars inherited more of these metals, making it easier to form complex planetary systems. The Sun would be part of this later generation, a star rich in the ingredients necessary for life. Meanwhile, the galaxy itself continued to evolve. The gentle tug of gravity from nearby galaxies, especially Andromeda, subtly shaped its outer structure. Streams of ancient stars, remnants of dwarf galaxies consumed by the Milky Way, still orbit through its halo, ghostly reminders of its violent youth. Our galaxy is not unique, but it is our home, a vast island of light in a sea of darkness. Every star we see in the night sky belongs to this one enormous spiral, and every element in our world was once part of its swirling clouds. About 4.6 billion years ago, in a quiet corner of one of its arms, gravity began to act once more. A region of the interstellar medium, enriched by the deaths of ancient stars, started to collapse under its own weight. Within that collapse, a disk of gas and dust formed around a growing central mass. That central mass would soon ignite as a star, our Sun, and around it, the dust would begin to clump into rocks, worlds, and eventually, a blue planet teeming with life. The story of Earth was about to begin, inside the solar nebula, the swirling cradle of our entire solar system. Around 4.6 billion years ago, in a quiet arm of the Milky Way, a vast cloud of gas and dust began to collapse. This cloud, a molecular nebula, was cold, dark, and immense, stretching for light years across space. Within it lay the ashes of countless ancient stars, hydrogen and helium from the Big Bang, carbon and oxygen from red giants, and silicon and iron from long-dead supernovae. Something, perhaps the shock wave of a nearby exploding star, disturbed the cloud's delicate balance. Under its own gravity, the cloud began to contract, and as it did, it started to spin. Conservation of angular momentum dictated that as the cloud shrank, its rotation sped up, much like a skater pulling in their arms. This rotation flattened the cloud into a swirling protoplanetary disk, the solar nebula. At the center of this disk, matter crowded together ever more tightly. As particles collided, compressed, and fused, the temperature soared. When the central region became dense enough, pressures reached levels where nuclear fusion could ignite. The Sun was being born. The young protostar that would become our Sun shone dimly at first, hidden behind a shroud of dust. But as fusion in its core stabilized, turning hydrogen into helium, it entered its main sequence phase, blazing into light. The newborn Sun's radiation and stellar winds swept outward, clearing away much of the remaining gas and dust from the inner regions of the disk. What remained would become the raw material for the planets. Meanwhile, in the swirling outer disk, tiny solid particles, microscopic grains of rock, ice, and metal, began to collide and stick together through static forces. These grains grew into pebbles, then into boulders, and eventually into kilometer-sized bodies known as planetesimals. It was within these collisions that the seeds of planets began to form. The solar nebula was not uniform. Closer to the Sun, temperatures exceeded 1,500 Kelvin, too hot for water, methane, or ammonia to exist as ice. Only metals and silicates could condense here, forming the basis for the rocky inner planets, Mercury, Venus, Earth, and Mars. Farther out, beyond a region called the frost line, it was cold enough for ices to survive. Here, massive cores of ice and rock could accumulate thick envelopes of hydrogen and helium, giving birth to the gas giants Jupiter and Saturn, and the icy worlds Uranus and Neptune. Throughout this process, turbulence and gravity sculpted the disk. Jets of material erupted from the young sun's poles, while the outer regions remained shadowed and cool. Magnetic fields intertwined with charged particles, shaping the flow of matter. It was a cosmic construction site, violent, dusty, and spectacular. Within a few million years, the sun stabilized and the surrounding disk began to thin. The once chaotic nebula transformed into a system of emerging worlds, each tracing a path around its glowing star. Among them was a small region of rocky debris, orbiting about 150 million kilometers from the Sun, the zone where Earth was taking shape. The solar nebula theory, supported by observations of countless young stars with similar disks, such as those seen by the Hubble and James Webb Space Telescopes, remains our best model for understanding how solar systems form. Each one is a replay of that same ancient process, gravity turning chaos into order, dust into worlds. The birth of the Sun marked a new era. From this swirling disk of fire and dust, the planets would soon coalesce. And amid the heat and collisions, one of them would someday cool enough to harbor oceans, continents, and life itself. But before that world could exist, the Sun had to truly awaken, igniting its nuclear heart and setting the stage for the next act in our cosmic story.